I'm Frances Hellman. I'm a professor and chair of the physics department. And I'd like to welcome you to the first of what will, I believe, be many public lectures sponsored by the Berkeley Center for Theoretical Physics. So this center, and I think many of you were just at the reception for this, was formed to bring together some of the greatest minds in theoretical physics to search for answers to some of the most pressing questions about the universe. And our speaker today is an illustrious example of one of those minds. So events like this lecture are part of the mission of this center to not only bring together those minds, but to bring some of that science out to the public as well. So I'd like to give you a brief biographical sketch of David Gross. David Gross received his bachelor's and master's degree from the Hebrew University of Jerusalem in 1962. He received his PhD in physics from UC Berkeley in 1966, then spent 3 years as a junior fellow at Harvard. 1973, he became professor of physics at Princeton. He then assumed the title of director and holder of the Gluck Chair at the Kavli Institute at UC Santa Barbara. He has made many, many profound contributions to physics, but is known particularly for his work on what is called the asymptotic freedom of quarks. Quarks are the fundamental particles that make both neutrons and protons, among other less well-known particles. The interactions between these quarks are what causes the protons and neutrons to form and what causes the strong nuclear force that binds these together in the nuclei of atoms. David's work, which was done in 1973 together with Frank Wilczek at Princeton, discovered the nature of these interactions, and that in particular that the interactions between the quarks depended very strongly and very not intuitively, I have to say, on how far apart they are from each other. When they're far apart, they're pulled together extremely strongly, so much so that they cannot escape each other. So the consequence of that is that we do not observe single quarks, despite the fact that we are quite confident that they really exist. But when they're very, very close together, the interactions are so weak that they behave as free particles. So this theory actually underpins virtually all current models for how nuclei work and fundamental particles and et cetera. He's won a really large number of prizes, awards, and honors, and there's one particularly that he's known for. And I'm sure many in the audience think they know what it is, but I'm willing to bet that you actually don't. So I'd like to point to the fact that in approximately, I'm going to guess, somewhere between like 1964, he was one of 800 students arrested during the sit-in at Sproul Hall. So we're very, very proud of all of our Berkeley students and very proud of their long and illustrious history. Incidentally, he also won the Nobel Prize in Physics. And that Nobel Prize was given for his work on the asymptotic freedom of quarks. So his talk today is actually not looking backwards, I'm told, at that work, but is looking ahead instead at the coming revolutions in fundamental physics. And so with that, I would like to ask him to come up and we'll thank him again.
Can you see this? Well, thank you, Frances. It's really a great pleasure to be back in Berkeley. Sorry? Anyway, it's really a great pleasure to be back in Berkeley, where my real life in physics began 45 years ago when I arrived as a young graduate student. Berkeley at that time was incredibly exciting. It was the center of particle physics. The highest energy laboratory was at that time still at Berkeley. And theoretical particle physics was enormously exciting. As Frances remarked, Berkeley was exciting in many ways at that time. But for me, most of all in physics. It's a delight to be back here. Some of my thesis advisor, my teachers, Professors Chu and Mandelstam are in the audience. Some of my fellow graduate students, John Schwartz, Ling-Li Wang, and I'm not sure whether there are others of our generation, but it's really delightful to be back. I really owe a lot to Berkeley, and I was happy to repay it partly a few years ago when I served on a review committee that reviewed the Berkeley Physics Department and came down very hard on the Berkeley administration for not supporting enough this jewel of physics in the United States. As a consequence of that, within 2 weeks, the administration gave Physics Department $12 million. Which they've used to create this incredible center that we all saw, or some of us saw this afternoon, which will help continue the great tradition that Berkeley has played in American science, and especially in theoretical physics. So I did my part in getting the 12 million. They still need a lot more, it seems. And I appeal to those of you who have the means to contribute as well to the success of the Berkeley Physics Department and the Center for Theoretical Physics. So I'm going to talk today about the coming revolutions in fundamental physics, and I'm going to briefly discuss the state of particle physics and the discoveries that we expect are around the corner when the Large Hadron Collider, a large particle accelerator, is completed next year at CERN in Geneva. But mostly I'm going to be talking about string theory, which I'm sure you all have heard of. This crazy idea that things are made out of strings. I'm a collector of popular opinion about string theory, especially cartoons. And years ago, in about 1987, I really was happy to see that the New York Times regarded string theory as something very difficult, but interesting and clearly very important. This couple, she's saying, it's all string theory to me. I was happy that string theory had replaced Greek. But recently, string theory is, because of some rather silly books, has gotten a different reputation. And the same New Yorker magazine had this cartoon in 2007, Harvey's Place. There is a discussion on string theory. This depressed me quite a bit until a friend of mine sent me this advertisement that he found in the New York Times magazine for lingerie. String theory. When physics gets physical. Restored my confidence in the American media. So, particle physics. We have an extraordinarily successful theory of particle physics. The culmination by the end of the 20th century of a quest that has gone on since Democritus for over 2 millennia to understand the nature of matter. And that quest proceeded, as you know, in discovering that ordinary matter is made of atoms, point-like objects that form larger objects due to the forces between them. But in the 20th century, we understood that atoms themselves had structure and consisted of a point-like nucleus and surrounded by a cloud of electrons. Electrons being the first of a family we now identify as the basic constituents of matter, leptons. The nucleus, apparently point-like at first, was also revealed in the later in the 20th century, and especially after the war, to have a structure itself made out of point-like particles, protons and neutrons, which later in the 20th century were revealed to have a structure, as it turned out, to be made out of point-like quarks. And that's sort of where the story ends at the moment. As far as we understand, all the matter we've ever seen in the laboratory is made out of quarks, and which form nuclei. Leptons, like the electron, that revolve around the nuclei, they form atoms in ordinary matter. We've discovered different types of quarks, in fact, and leptons, 3 families of quarks and 3 families of leptons, the electron and the elusive neutrino. So by the end of the 20th century, we seem to have identified all the kinds of matter that we need to explain all the stuff that we've ever created or observed in the laboratory. And we explain it in terms of understanding the forces that act on these basic elementary atomic constituents. The forces are, of course, the force of electricity and magnetism, which holds the electrons in orbits around the nucleus, and the 2 nuclear forces that act at very short distances within nuclei and within nucleons. The strong force that holds the quarks together permanently within nucleons and provides the source of the nuclear force. It's a strong, much stronger force than the electromagnetic force, which is why hydrogen bombs are much more powerful than TNT. And of course, there's another force in nature that all of us are acquainted with and was understood way back by Newton and improved on by Einstein, the force of gravity, which at the atomic level plays very little role. These 3 families of matter, leptons and quarks, and these 4 forces constitute what we might call our standard model or standard theory of elementary particle physics, of fundamental physics, of the fundamental constituents of matter and the basic forces that operate on these fundamental constituents. And as far as we can directly tell by observation, the standard model of the electromagnetic weak and strong nuclear forces, plus general relativity, Einstein's theory of gravity, is the theory of all the observed forces of nature. And it is an incredibly successful theory. It is not as widely appreciated by the general culture as it should be. What an incredible achievement of physics this has been after 2 millennia. This theory has been tested down to extraordinarily short distances of order 10 to the minus 18 centimeters. Some of my colleagues work on nanophysics, a branch of physics defined by size, the size being 10 to the minus 9 meters. Well, particle physics works at distances of nano centimeters and tests our theories down to such distances and with extraordinary accuracy. The tests of this theoretical framework, which is based on quantum mechanics and on local field theory, quantum field theory, has been tested now to, in some cases, an accuracy better than a part in a billion, which means you can both measure and calculate a number, a measurable quantity, and you have to worry about the 10th decimal place. It is unbelievable feat of both experiment and theory to achieve such accuracy. But all of the components of the standard model, not just electromagnetism, including the weak and strong nuclear forces, have now been tested in dozens of cases to accuracies of much better than 1%. We also see no limitation of this theoretical model. Sometimes you construct theories they contain within them the seeds of their own destruction. They lead to paradoxes, to problems. You know that they have to go wrong at some scale. Well, the only place that we know that this theory goes wrong is the so-called Planck length of 10 to the minus 33 centimeters, an incredibly short distance. This framework might explain all of physics down to that length. We see no reason why it must fail before then. And since the same theoretical structure works at the level of planets and stars and galaxies, indeed the whole universe we now describe using the standard model, particle physics and general relativity, we can say that this theoretical framework works from the Planck length to the edge of the universe at 60 orders of magnitude. On a logarithmic scale, we are halfway between the Planck length and the size of the universe. And we have one theory, one theoretical framework that seems to be able to explain all of this. This might lead one to conclude that with such great success, particle physics, high energy physics, or what I call fundamental physics, the search for the basic constituents of matter and our understanding of the basic forces that act on them is over. But of course, the very success of the standard model, our very understanding that we've achieved, raises more questions, or as many interesting questions that it answers. I like to say that the most important product of knowledge is ignorance. Not the kind of ignorance that leads to political strife, bigotry, racism. That's not the kind of ignorance I'm talking about. I'm talking about the ignorance that leads you to ask why questions. The ignorance that is the basis of scientific exploration. The ignorance that we cherish, informed, intelligent ignorance that is based on deep understanding of what important, interesting, addressable scientific questions are. And that ignorance requires knowledge, and the standard model has produced such wonderful ignorance, wonderful questions. Questions like, why are all these forces, the forces that we observe in nature, electromagnetism, weak, strong, nuclear force, all have their origin, we believe, in a notion of symmetry, a beautiful symmetry principle, a local symmetry we call gauge invariance. Now, there are many other kinds of forces that we can imagine, but somehow local symmetry seems to be the secret of nature. Why is that? And then there are all these different forces. They look kind of different. And why are they different? And they're characterized by different strengths. And why are the strengths of the forces what they are? Now, these are questions that you can't begin to ask until you understand what the forces are and how they work. And that we do. But now we're driven to ask these questions. And others we have discovered, measured, observed these various families, the basic constituents of matter, quarks and leptons, and they have a strange and bizarre pattern of masses and mixings. And we've been measuring with great precision these masses and properties of quarks and leptons for the last 40, 50 years. And so far we haven't been able to discern any obvious pattern, and certainly no explanation of their strange pattern of masses and mixings. So why are there three families, and why are they have the values that they do? And now that we're beginning, as we'll see, to incorporate gravity, the dynamical theory of space and time, into our considerations, we begin to ask questions that when I was a student here were regarded as philosophy and not physics, but now are physics, such as why is space three-dimensional, or is it? Maybe there are 9 or 10 spatial dimensions. Why? This is what drives physics forward, and the the why questions we ask now are much more interesting than the why questions that were asked 45 years ago when I was a student here. Many of those we answered, but these are still around. And of course, we'd like to answer them because we're curious. We'd like to know, can we answer them? Some people, we'll see, argue that not all of them are answerable or calculable. But it's more than that. We need to know the answers to these questions to really understand the beginning, the origin, and the early history of the universe. Particle physics has constructed a standard model that explains almost everything we observe, but so has, in recent years, astronomy, astrophysics, and cosmology. We have learned an enormous amount about the history of the universe depicted in this rather complicated history, starting with a big bang, inflating rapidly, settling down to a almost constant expansion, starting in a very hot stage and dense, and then cooling off as the universe expands. We have directly observed much of this history, indirectly understand even more, and have a picture that is quite satisfying. It fits together a standard model of astrophysics and cosmology from close to the beginning, whatever it was, till now. Of course, now the physics we see around us is physics of atoms that make up stars and galaxies and people. But in earlier times, which we can observe directly by seeing light that comes to us from far away, and therefore in the past, we can see eras where totally different physics applied. If we go back to about 300,000 years after the beginning, back in time from 13 billion years where we are now, we reach the era where we can no longer see directly beyond. At that point, the universe was so hot that atoms were stripped of their electrons and lived in a plasma of electrons and nuclei and radiation, a fog that prevents light from escaping. So before that, we can't directly observe the physics, but indirectly we can, using our very good theory, understand that in previous eras, like, for example, 100,000th of a second after the Big Bang, we believe that before that time, the universe was so hot that nuclei actually melted and quarks escaped from their confined nucleons. And one had a plasma of quarks and gluons and electrons and radiation, a state of matter which is of great interest and one that we are trying to reproduce directly in the laboratory by smashing heavy nuclei at high energies to create a quark-gluon plasma that might live for a short time and be observable. If we go back even further, however, we believe that our understanding of the physics inevitably will break down, and yet it was crucial to the formation of the structure, the fluctuations in the matter that led eventually to structure and the formation of galaxies and stars. If we go back even further, we arrive at the beginning, the Big Bang, that produced, it seems, a very rapid inflation of the universe, and all of our equations break down. Well, one of the roads that people have tried ever since the standard model was completed in the 1970s to try to answer these why questions that don't seem to be answerable within the standard framework was to search for unification, Einstein's dream of unifying all the forces of nature together. And it wasn't just because of the belief that a unified theory would be more predictive, more powerful, more able perhaps to answer some of those why questions. It was also because the very pattern of force and matter that was discovered in the standard model, the three forces that act within the atom, electromagnetism, weak and strong nuclear forces, and the two kinds of matter are pieces of a jigsaw puzzle that fit very naturally together. It was realized very early on that the three forces fit together as if they really are part of a single force. Each of these forces arises because of a symmetry of nature, we learned. And they seem to fit together as if all of them arise together as a consequence of an even bigger symmetry of nature. And the same with the matter. The matter fits together beautifully as a representation of that symmetry. It's as if we have one force of one atomic force and one form of matter, where all of the quarks and leptons fit together into a representation of the basic symmetry group that underlies all of the forces. But this is a bit strange because, after all, if all the forces are equal, they would look equal. If they came from a bigger symmetry, we would have noticed the consequences of that bigger symmetry. And the only reason we can imagine such a unification taking place is because of two great lessons that we learned in constructing the Standard Model. One from the success of building the electroweak theory, our understanding of electromagnetism and of the weak nuclear force, that symmetries can be broken, not manifest in the real world, in the state of the world, although symmetries of the laws of nature. And the other is that could explain, the other phenomena is related to the asymptotic freedom that Francis mentioned. She explains how the forces could be the same even if they have very different strengths. The force of electricity and magnetism is much, much weaker than the nuclear force. How could they be the same force? Well, that was related to our understanding that the strength of forces in quantum theory depends on distance. It could be the case that all of these forces are equal, not at the largest, if you think of the size of a nucleus as large, distances we now probe, but at much, much smaller distances. Why is it that the strength of the forces depends on distance? Well, that has to do with the properties of the vacuum. This is a picture of the way many of you might think of the vacuum. This is the classical vacuum. The classical vacuum is empty. That's what it looks like. Remove everything from this room, all the people, all the chairs, all the air, everything. Cool it down to absolute zero. You're left with the vacuum, which looks like this. That's the classical picture of the vacuum. But in quantum mechanics, that's not what happens. According to Heisenberg's uncertainty principle, you can't have anything inert, anything dynamical. And remember, all of space-time is full, potentially full of electromagnetic, strong and weak nuclear fields that transmit the forces between the particles. Those fields can't be quiescent and in their ground state, motionless, inert, in the vacuum as classically one might imagine, because if you tried to observe the vacuum, you would disturb it and set those fields, those dynamical objects in motion. A pendulum classically can sit at rest, but quantum mechanically, if you observe it, you give it a kick, so it must always be moving, what we call zero-point motion. Here is a picture of the quantum vacuum. And we know it's an accurate picture because we have a theory that works, at least at nuclear scale. So here is a picture of the quantum vacuum as calculated using our theory of the strong nuclear force, quantum chromodynamics. which gives the dominant contributions to what's going on in the vacuum at length scales of a nucleus, which is 10 to the minus 13 centimeters. This is what the vacuum looks like. Those fluctuating stuff are the quantum fields that give rise to the nuclear force between quarks. So the vacuum looks like this, not that empty white space. It is a dynamical medium, a complicated place. And in such a medium, the force between two objects carrying some charge and interacting through these very fields that are fluctuating can depend on the distance. Just as a dielectric medium like water can screen electrical charge. So that's what happens. And that has the effect, in the case of the strong nuclear force, of leading to the fact that as we go to higher and higher energy of the quarks that interact with this strong force, the force gets weaker and weaker. High energy corresponds to short distances. So going to high energy is the same as looking at a physical phenomena at short distances. Which is why you need very high energy beams like to probe short distances. This diminution of the strong force as a function of energy or distance is what was referred to as asymptotic freedom. Well, if this is the case, then the strong force gets weaker at high energies or short distances. Maybe it could become weak enough to be comparable to the electric force, and they might have a common origin. So if we look at the standard model, we have these three nuclear forces, three forces that act within the atom and the nucleus, the strong, weak nuclear forces, and electromagnetism. And over the range where we observe today, they all vary with energy, roughly in this manner. And we can use our theory to say how they vary with energy at higher energies. We can extrapolate the standard model. And what was discovered early on was that these forces seem to come together as if they were a single force, but only when you look at very high energies or very short distances. They split because of this phenomena of symmetry breaking. But if you were to do experiments at this extraordinarily high energy, 15 orders of magnitude higher than present-day observation, you would see evidence that they were unified. This was a very important, and remains a very important clue to, one, the unification of all the forces of nature, and second of all, the extraordinarily high energy scale at which they might unify. It's a bit depressing, and it has been for years. It still is depressing, because we are not going to have a chance in our lifetime, if ever, to do direct measurements at this scale of unification. But that doesn't mean that there's not a lot of wonderful physics that might appear in between at lower energies, which are accessible. And in particular, we're most interested today in what might appear at the Large Hadron Collider, which pushes present-day observation by about 1 order of magnitude. And here some of us expect a true revolution to occur, which is the discovery of something called supersymmetry, one of whose inventors, Bruno Zimino, I think is in the audience. So I want to say a word about supersymmetry. That's the first and most upcoming experimental revolution that some of us think might be discovered in a few years. And to discuss what supersymmetry is, I need to tell you what superspace is, because the best way of describing a symmetry is to describe the space on which the symmetry operates. So an example of a symmetry is rotational symmetry. As you know, the laws of physics are rotationally invariant. That means if I do an experiment like I drop this, measure how long it takes, and then I rotate the laboratory and I do the experiment again, I get the same answer. Laws of physics are invariant under spatial rotations. I rotate the x-axis into the y-axis. So to explain a symmetry, easiest way is to explain the space on which the symmetry transformations act. And in the case of supersymmetry, it's superspace. So what is superspace? Well, you all know what space-time is, right? In ordinary physics, we measure the position of a particle and the time of an event by a point in space-time. We have x, y, z, spatial coordinates, and time. So to describe superspace is a space with more dimensions, more coordinates. We need more coordinates to say where a particle is. We have these extra so the symmetries, for example, rotational symmetry was rotating x to y. Superspace has some extra coordinates, which I call theta here. We use Greek letters because we measure these coordinates with a new kind of number, different kind of number than we measure these coordinates. So if I measure distances in this direction, we use ordinary numbers, 1, 2, 3. In this direction, we use funny kinds of numbers called Grassmann numbers, variables. And they have the property that if you multiply two of them, theta 1 times theta 2, you get the opposite answer than if you multiply them in the other order. Theta 2 times theta 1 is minus theta 1 times theta 2. They anti-commute. They are not a commutative under multiplication. Well, mathematicians can invent all sorts of crazy numbers. Square root of minus 1, right? That's pretty crazy. And these are kind of nice numbers. I mean, multiplication table is very short because theta 1 squared is 0 because it's equal to minus theta 1 squared. So these are consistent kinds of numbers that you could invent. And it turns out that there is a generalization of ordinary space-time where you add extra coordinates, new dimensions, but not new dimensions of the usual type, but new dimensions where you measure the dimensions in with these anti-commuting numbers. There's a beautiful generalization of space-time. And there's a beautiful generalization of the symmetries of space-time, where in addition to rotating x to y, you can also rotate x to theta and theta to x. Mathematicians actually didn't discover that. It was discovered by physicists. And as we'll see, the first hints came from string theory. But it's a beautiful extension of the traditional notion of space-time and of the symmetries of space-time that underlie our understanding of the physical world. Relativistic quantum field theory, general relativistic theory, which underlies gravity. Again, is beautifully generalized to superspace, which has these anti-commuting coordinates. In physics, we have two kinds of particles in nature, bosons and fermions. They differ by their spin, integer spin, angular momentum, rotation, or half angular momentum. They differ by their statistics. Bosons are things that sort of commute, like x's. Fermions are like thetas that anti-commute. You exchange two fermions, you get a minus sign in our description of the physics. And so these kinds of rotations change bosons into fermions, fermions into bosons. When you have a theory of nature formulated in superspace and the laws of physics are invariant under that, then under rotations in superspace, then these transformations lead to the remarkable prediction that for every particle you've ever seen in the ordinary kind of theory, there has to exist a superpartner you get by making one of these new transformations. So the immediate consequence of imagining that our world is supersymmetric in some sense would be that quarks, which we observe, would be accompanied by something we call squarks, which are actually bosons of spin 0, and electrons would be accompanied by things we call selectrons, photons by photinos, and so on. Everything you've ever observed, you have a superpartner, which we've never seen. And you might say, therefore, this idea mathematically is beautiful, but physically is absurd. But we've learned, as I get coming back in the 20th century, that many of the symmetries of the world, certainly some of the symmetries that underlie the Standard Model, and certainly if there are unification based on bigger symmetries, those symmetries are not manifest in the world around us. Now that's a common phenomenon. If you look at this room, it is not rotationally invariant. If I look that way, I see all of you. I rotate, I don't see you. The laws of physics are invariant under rotations, but this room isn't. Well, this room is a complicated place. We put all these people here, chairs there and not there. What about I remove everything from the room? Will it look rotationally invariant? Well, if you thought of that, that's getting back to the vacuum. If you thought of the vacuum as being this empty white sheet, yeah, it looks rotationally invariant. You rotate the sheet any old way. But think of that vacuum as that complicated mishmash of fluctuating fields. It need not respect the symmetries of the law of nature, just as this room doesn't. So we can invent new symmetries, new spaces and symmetries on which they act, which act on those spaces. And if the symmetry is broken, then these particles, new particles that are predicted to be there with the same masses as the previous ones, could be very heavy. And if the symmetry is broken with a scale of about 1 trillion electron volts, then these particles, although heavy, can be produced at this new accelerator. Well, this is very pretty, and it is very pretty, but why should we expect this to have any chance of being seen? Well, there are 3 important clues that we have that supersymmetry might be there, and it might be just around the corner. First, it actually helps us with that unification of the forces. If we looked at that unification, it doesn't really work. Here, this is a plot, a logarithmic plot of inverse couplings, which are straight lines on such a plot. And if the unification really worked, these straight lines would meet at a point. By now, our experiments have improved so much, and the theory as well, that the extrapolation has gotten quite good, and you can, within the Standard Model, these forces, if there's nothing else, don't meet, no unification. On the other hand, if you just take the Standard Model and assume it's part of a broken, not manifest, supersymmetric theory in the minimal fashion, and you assume that that breaking is at a TeV scale, then again, you can do the extrapolation. There's a change when supersymmetry kicks in, and the forces meet precisely at a point, more or less, within better than 1% accuracy after extrapolating over 14 orders of magnitude. That is, in my opinion, an extremely strong clue that unification is correct and supersymmetry is correct, and the scale of supersymmetry breaking is down here, just where we might observe it. It might be a coincidence. Supersymmetry also helps explain the hierarchy, this enormous ratio of scales between the unification scale and the electroweak scale, the scale of the weak nuclear force. That's a very small number. That's why the unification scale is so far away from present-day observation. We think we can explain this very small number, but we need something and some extra symmetry to help us. Supersymmetry does it. These 2 features of supersymmetry, by the way, were not the reason people invented supersymmetry. Supersymmetry happened to cure these problems. And most remarkable is, again, a realization after supersymmetry had been around, that there is a lot of matter in the universe which we don't understand what it is. It seems to be a new form of matter. It's called so-called dark matter, which I'm sure you have heard constitutes most of the matter in the universe. Galaxies don't really look like this. Our normal picture of a galaxy based on the stars that we see, the light matter, the matter that interacts with light and we see. Astronomers have concluded by measuring the orbits of these stars in the galaxy that there's not enough mass in the stars to hold the stars in orbit. There has to be a lot of other mass, a lot of other matter. And they can deduce how much there is, and 90% of the matter in the universe appears to be in the form of some kind of very heavy particle that doesn't interact very strongly with our kind of matter and light. Now, we don't know what that dark matter is, but in supersymmetric theories, there is naturally a candidate for it, which, if the scale of this heavy new particles is where we can produce them at the LHC, we can understand why 90% of the matter in the universe is dark. So these are three indirect, but in my opinion, very compelling clues to take this possibility of this symmetry very seriously and to look for the LHC, this incredible new accelerator that is being completed in Geneva, runs between Switzerland and France and bangs protons together at trillion electron volt energies. This machine, with its unbelievably massive and complex detectors, has a chance of discovering this super world. This is a revolution if it happens, because, and when you read in the paper a few years from now that physicists at CERN have claimed to have discovered supersymmetry, you should remember that this is a symmetry of superspace, and that discovering this symmetry, non-manifest or broken, as we say, doesn't matter. It really means that the world has quantum dimensions, that we live not just in ordinary space-time, but we live in superspace. So discovering new quantum dimensions of space-time I regard as a major revolution, and that might be around the corner. But, this is still a bit disappointing, because if we discover supersymmetry, we're still not going to know directly what goes on at the unification scale. But here we have one more clue, which we haven't mentioned yet, and that's gravity. Gravity is a totally ignorable force in atomic physics, in nuclear physics. Sometimes I find it hard to explain to people that gravity is unimportant because it's the only force they know about. It's the force they feel when they wake up in the morning and get out of bed, or when they fall flat on their face. The other forces are shielded, like the electromagnetic and weak and strong forces. All objects are neutral because the forces are so strong, most of the time. But gravity, everybody feels, but it's incredibly weak. And the best, if you wanted to demonstrate that to someone who doesn't realize how weak gravity is, just hold something up and tell them that you are exerting a minute amount of electrical energy, electrical chemical force, to hold this up, even though the whole Earth is pulling down on it. So I can easily oppose the whole Earth, the attraction of 10 to the 53 protons in the Earth, by exerting a little bit of a much stronger, by 40 orders of magnitude at the atomic scale, electrical force. But gravity increases rapidly as you go to higher energies. two particles moving past each other at very high energies have an increased gravitational force, which after all, gravity is the force between mass. It's proportional to mass squared. And mass, of course, E equals mc squared is energy. So gravity rises quadratically as you increase the energy, whereas these forces vary logarithmically. And if you go up by 20 orders of magnitude, gravity becomes equally strong at the atomic level, at this very small so-called Planck scale to the other forces of nature, at just about the place where they unify. And that is a very important hint. The hint is that if we're going to unify the strong, weak, and electromagnetic forces that seem to fit together so neatly, we're going to have to unify them together with gravity, which was Einstein's dream. But this picture tells us that, we're driven to that. And that is a serious constraint, because you can imagine many ways of trying to unify strong, weak, and electromagnetic interactions, and people did for years. But gravity is a different story. That's much harder, and that brings us to string theory. Quantum gravity doesn't really fit into our framework, it seems. If we try to incorporate Einstein's theory of gravity in the framework we use to describe the other forces, we run into problems. Einstein taught us that gravity is the dynamics of space-time. So we have the object, the gravitational field, is really the metric, the distances of space-time itself, the very structure of space and time. And like anything else in quantum theories, that fluctuates all the time, like that picture of the vacuum. And so space-time is fluctuating, and it seems that in Einstein's theory, if you just blindly quantize it, try to make a quantum theory out of it, the fluctuations are uncontrollable. They're uncontrollable at these very short distances. And nobody was ever able to control them. Which might mean that, well, we just weren't smart enough, or that Einstein's theory is only an approximation. We have to go beyond it to some other theory that is perhaps more fundamental and reduces to Einstein's theory at large distances where we use it so far. And string theory is such a theory. It goes beyond Einstein's theory, much in the same way that Einstein's theory goes beyond Newton's theory of gravity. Newton's theory is pretty good when you want to throw things up in the air in this room, but they're small corrections, and they can become big in certain circumstances, and the same thing with string theory. And string theory is a break with this past of point-like constituents making up matter that has worked so well from atoms down to quarks and electrons. In some sense, string theory breaks with that by saying that if you were to look very carefully, imagine a microscope that could resolve this very small Planck scale distance, you would see that quarks and electrons are vibrating strings. And in fact, since a string vibrates in many different ways, the quark and electron turn out to be different vibrational modes of the same string. Not only that, but all of the particles, not just the elementary particles of matter, but the elementary quanta of force, which are particle-like as well. The photon, the particle of light, the graviton, the particle of gravity. All particles in string theory, in some sense, are different harmonics of the same string. It's a beautiful unifying idea. So what is string theory? Well, we don't actually know the answer. String theory is sort of accidentally discovered and developed, and it's far from a complete theory. But the way so far that it's developed, it is what I like to call a conservatively radical modification of the principles of physics. It is very dangerous to try to modify the principles of physics. It's not dangerous to modify models of areas of science where we understand the basic fundamental laws. But it is very dangerous to modify the principles of physics. You're of overwhelming likelihood to be wrong, logically inconsistent with experiment, or logic, or both. If you're going to modify anything, you should modify as little as possible. And to some extent, string theory so far has modified very little of our traditional theoretical principles of physics, if any. It replaces particles by strings. It says, well, we're not going to make things out of particles, we're going to make things out of strings. Well, why not? But every other principle of physics so far has been left unchanged. I'll argue later that that's not going to be enough. But that's so far what's happened. And the way that we've constructed this theory over the years, and string theory is, next year will be 40 years old, is to essentially take everything we know about particles, quantum field theory, the basis of the Standard Model, and do the same for strings using the same principles. So for example, we discuss the motion of a particle, and we like to understand how a particle moves. Well, we draw the trajectory of the particle moving in space as time goes on, and we can determine that motion by various ways. One way is to find the minimum length path that leads to geodesic motion of a free particle. It's a nice way of describing the laws of motion classically of a particle. And we can do the same with a string. A string moves, sweeps out a tube. Tube doesn't have a natural length, but it has the generalization, area. We minimize the area or extremize the area of the world tube of the string. You get the motion of a classical string. It's really totally straightforward, nothing new. Once you have this classical picture, you can easily do quantum mechanics, because Feynman told us that in quantum mechanics, you simply sum over all trajectories, all paths. And if you want to calculate the probability for the particle to go from this event A to this one B, you sum over all paths. You weight the path with a phase, which is proportional to the length. You square that amplitude to get the probability. That's Feynman's picture of quantum mechanics. Do the same for strings. You consider not just one tube, but all tubes. You sum over all of them, and you weight the sum by the exponential of the area. Totally straightforward, nothing new. Mathematics is a little more complicated. But in 100 years, it'll be taught in high school. The remarkable thing happens, however, when you consider string interactions. Here there's a surprise. Feynman tells us, how do we describe interactions? Well, we have a particle A and particle B. They move along these trajectories. Quantum mechanically, you sum over all trajectories. If they happen to be at the same point at the same time, they have some probability of turning into a third particle, C, at the interaction point. This is a nasty point. It's really a singularity of the graph. It's where all of the uncertainty and the unknowables of our theoretical framework lie. All of those numbers we can't calculate have to be put in at these points to specify the probability that A, B turns into C. This is where all of our why questions lie. Anyway, that's what you do with particles. So with strings, you have to blow up this picture to go from lines to tubes, but there are two ways of doing it. You could have string A and B, And they could interact by coming together, just like the particles, overlapping and forming a new string, C, which goes off, which gives rise to this picture. We've blown up those lines. A and B come together, form C, which goes out. This would have been a disaster if people had constructed string theory this way. You would have had to specify probabilities for this to occur for each curve. There are an infinite number of curves, an infinite number of parameters that you couldn't determine, would have to specify. Furthermore, this would have been fraught with other divergences and sicknesses. But there's another way. These two strings can move along, come together, and turn into a third string. Very different picture. And that leads to a diagram which is called the pants diagram. So here we have the two strings coming together, overlapping completely. This is awful. Luckily, no one ever considered it. No one ever considered it, by the way, because when they were constructing string theory, they never knew they were doing string theory. They were playing around with mathematical formulas. What they constructed was this way of string A and B turning into string C, like the sections of your pants as you go up. Two cuffs turn into a string. If the pants are well made, there's no singular point on the pants. There's no place where the interaction occurs. There's nothing to insert. In fact, once you know how to make the cuffs, you know how to make the whole pants. You can only tell by looking at the end whether you have one string or you have two separate strings. It's a remarkable thing, this kind of interaction from this point of view. It's sort of unique, topological. There's no place you can insert additional information. That offers the tantalizing prospect of being able to calculate everything. There are no free parameters. It also means you can't change anything in string theory. You get what you get. Once you know how to describe free strings, you know how to describe interacting strings. Now, of course, it's not so simple because this is sort of a perturbative. You start with free strings and then they interact once, they interact twice. It's a perturbative way of constructing, and that's roughly how we understand string theory. A whole bunch of rules for constructing solutions perturbatively. But all of them are essentially unique if you have a good starting point. Totally remarkable, and the first time in physics. String theory has amazing properties, all of which I think are connected to that basic fact. It actually started not as an attempt to unify all the forces of nature, describe quantum gravity, but rather to describe the nuclear forces. And today we understand that because we understand how the nuclear forces work. And we can calculate. And this, again, is a picture of two quarks, two very heavy quarks, which I'm holding there close together, where they barely interact. And then we pull them apart, and we can calculate what the fields, the chromodynamic fields that hold them together look like, or lattice gauge theorists can. And this is the picture, and you see that the forces and the energy, these fields, this blue stuff are the fields and where all the energy is, are confined to a kind of tube between the quarks, which is why they can't escape. It's like a rubber band. You can never pull it apart. Pull them apart completely. And that tube is sort of like a fat string. And that's why we now believe that such mesons made out of quark-antiquark pairs have properties that are string-like. And that's what led people, based on observation, to invent string theory. But then it turned out that there were all sorts of surprises that came out of the theory. Now remember, this is not a theory you can fiddle with. You get what you get. You have no choice, unlike any other time in physics, I must say. So when people encountered the fact that space-time had to have 26 dimensions or there were inconsistencies, they were disturbed because it didn't look like that, especially in the nuclear domain. Then they discovered supersymmetry, in effect, in order to have fermions like quarks, particles with half-integer spin. That reduced the number of dimensions to 10. Then they discovered that the theory had local interactions and symmetries, which now we understand is at the basis of the nuclear force, but not a property of the mesons. And then they discovered that the theory had to contain gravity, which they weren't looking for. They were just looking for a theory of the nuclear force. Well, luckily, when the theory of the nuclear force came along, string theory, by and large, was abandoned, except by some brave souls, pioneers like John Schwartz, who was in the audience, who persisted and extended. And recently, we've discovered many more amazing properties, which I don't have time to explain. We've discovered that string theory isn't really necessarily a theory of strings. There's an equally important role for other extended objects, brains, brains of various dimensions. And we've discovered an incredible array of totally different descriptions of this theory, whatever it is, all related to one another by an intricate web of so-called dualities, and much more. Well, string theory has achieved quite a bit, although it has also failed in substantial ways. Its achievements are that it is some kind of extension of the conceptual framework of physics, as I said. But so far, a sort of minor one, not on the same level of relativity and quantum mechanics. We've replaced particles by strings, but not much more at a fundamental level. But some of us still believe that what string theory will end up being will be an equal revolution to relativity and quantum mechanics involving the third dimensional parameter of physics, the Planck length, which is associated with gravity. It has provided us with a consistent finite theory of quantum gravity, which is very important. But most important, most intriguing, exciting, is that string theory has this incredibly rich structure. And it is, in some sense, extremely unique as a theory. So it seems to have the possibility of having all the ingredients that we think are necessary. We don't know of anything in the real world, Standard Model and anywhere else, that isn't contained naturally in string theory. And it's an incredibly unique theory. So I want to discuss the achievements before I discuss the failures. Quantum mechanics and gravity were hard to reconcile for 70 years. The fact that string theory provides a consistent theory that reduces to Einstein's theory for large distances and is consistent with quantum mechanics, is a quantum mechanical theory, is a proof that there's nothing inconsistent between general relativity of Einstein and quantum mechanics. But more important, it now provides us with tools to explore the truly paradoxical and weird issues that arise for strong gravity. A very hard task, but we now have the tools, and there have been some successes. The biggest success is the fate of black holes. A problem that was raised by Hawking, who noted that black holes quantum mechanically aren't really black. Treated by crude quantum mechanical tools, black holes act as thermal objects and emit thermal radiation. But he realized that that's a bit of a problem, because if you throw ordered stuff, if you throw stuff into a black hole and then it emits thermal radiation, you've lost something. You've lost information. And Hawking was so disturbed by being a relativist, concluded that the laws of quantum mechanics are indeed violated by general relativity in general, in particular for black holes, because this process violates the preservation of information, which is one of the main features of quantum mechanics. String theory truly saves the day here by giving us examples which we believe are representative of all black holes, but examples where we can precisely map this description of this process onto a theory where information is clearly preserved and seems to most of us to resolve this problem. In fact, even Stephen Hawking has agreed that he was wrong, that black hole formation evaporation will not violate the laws of quantum mechanics. But there are many other paradoxes in quantum gravity, in the regime where gravity is strong and the quantum effects are big that we don't yet understand. The most important one, of course, is the origin of the universe. Could string theory actually explain what goes on at the beginning? How could you possibly explain what goes on at the beginning? Well, this is one of the most important questions that we're studying, and clearly the answer so far is not yet, not at all. We don't yet understand. But we have the tools to continue exploring this problem, and it might take a long time. On the other hand, string theory also suggests, at least to some of us, that our very notions of space-time, which have been used so far in traditional gravity, relativity, and also in string theory, are going to have to be radically modified. What about the goal of producing a unified theory, answering those why questions, reproducing the standard model and calculating its parameters? Well, it's not easy. We seem to have all the ingredients, but to actually do the job, you'd have to do a lot. Since we can't do measurements at these very high energies, we'd have to understand lots of hard dynamical problems, like these extra dimensions of space. Why don't we see them? And this supersymmetry, which is so important in string theory, how is it broken? Because it must be. And then there's the problem of the cosmological constant. So briefly, these problems. The new dimensions might not be seen because they're very small. That's the traditional understanding, goes back almost 100 years to the imagining new dimensions that are curled up in little circles so you don't see them. Well, actually, in string theory, there's something like, at least in some ways of constructing approximations, 6 extra dimensions which we can learn about by trying to solve the analog of Einstein's equations for the structure of these dimensions. Get beautiful structures emerge, and in a way that would have pleased the Greeks, if you try to construct such solutions of string theory, the nature of the forces, what kinds of gauge forces emerge, the form of matter, the values of the masses are all determined by the geometry, the shape of these hidden dimensions. It's very beautiful. And there are approximate solutions, things you try to construct along these lines that look a lot like the physics we observe. However, it turns out there are zillions of other possibilities that emerge as approximate solutions as well, that don't look like what we observe. And then, finally, there's the cosmological constant problem. So remember, this is the vacuum. This is the empty state. This is the vacuum. The vacuum is full of all these fluctuating quantum degrees of freedom, these fluctuating fields. They move back and forth, and they all carry energy. All that motion has a lot of energy. That energy, mass, acts back on the metric of space and time. That's the theory, that's our theory of gravity. It's preserved, of course, in string theory, generalized, but this energy in the vacuum will act on geometry and will lead to a cosmological constant, which is the name for the vacuum energy. And such a vacuum energy has effects on the structure of space and time, leads to accelerated expansion or accelerated collapse in general. Now, if you naively estimate the cosmological constant of the fluctuating fields in the vacuum, the natural scale is this very high energy scale, and that leads to an enormous vacuum energy, one so enormous that the universe would have collapsed instantaneously or expanded so much that each elementary particle, each quark, each electron would be alone with no neighbors that could communicate with. Certainly not observed. This problem has been around in theoretical physics for almost 100 years. And in pre-stringy era, you tried to calculate this number. You didn't get 10 to the 120, you got infinity. Well, physicists have a very normal reaction when they encounter infinities in their equations. They simply put them equal to 0. They don't understand why, but they say, well, it can't be infinite, so it's got to be 0. Which was the attitude for years and years and years. Even in string theory, after we got a theory where there are no infinities, still it was too big, so it had to be 0. This is order of magnitude. Maybe there's some deep reason why it's 0. One of the attractions of supersymmetry when it was discovered for at least a week or two was the fact that because of a deep symmetry principle, the cosmological constant was 0. But then, of course, people realized that, well, it has to be broken, and that introduces a scale, and it's not 0, it's 10 to the 60. The attitude of most of us for years was, well, there has to be some reason why it's 0. Because it's too big, so there's a 0 someplace. Nobody had a reason why it was 0, but that was the attitude. This became more and more of a severe problem because you couldn't find a reason for the 0. And finally, as you know, the measurement of the cosmological constant was reported by astronomers. In fact, Perlmutter led one of the groups here at Berkeley, which observed the acceleration of the universe, which is presumably almost default explanation is cosmological constant, but very small, 10 to the minus 4 electron volt squared. So if that's true, we're not sure, but probably looks like it. It's much harder to say that it's 0, because it's been measured. Never understood why it was 0 anyway. So that's a big problem. And in string theory, if you try to construct a solution by this perturbative method of building up a solution where I described, you can calculate what lambda is, and you're going to end up with a value which is much like probably around here, no matter what you do. Well, this fact and the fact that there's so many different kinds of solutions of string theory, these perturbative constructions, have led people to the following scenario. Some of the people are in the audience, my colleagues. The landscape. The landscape is a picture of the possible solutions that you seem to be able to get out of string theory, more or less, with some confidence. And these different places in the landscape are different kinds of solutions. They have different shapes of these internal manifolds, of the compact dimensions, different forces, different matter, different masses, different cosmological constants. Now you add to that the idea of internal inflation of the inflationary cosmologists like André Linde and others, that this inflation that occurs makes our universe expand from a very small portion of a state that existed before, could have happened many times in a bigger multiverse. And you might end up, they say, in any one of these different states. Universe A, bad place, big cosmological constant. Universe expanded so rapidly, galaxies never formed. planets never formed. People were never there to ask the question, so we're not there. We're in universe B, where the cosmological constant happened to be, very unlikely, but happened to be small enough so that galaxies form, planets form, we form, we're here. That's why we're here. This is the anthropic principle. Unfortunately, I can't prove that it's wrong. But the main argument for it that is driving all of my otherwise rational colleagues is this: how could we possibly explain this incredibly small number? Or, or sort of what we observe to what we would predict. Well, I want to make a little side comment for their benefit. They haven't heard it, although some of them have, that we should be able to, it's not such a big deal. You really have to take the fourth root of this number, because then you get a mass scale. I mean, So this is the ratio of the scale of the cosmological constant to the scale of where we would have calculated. 10 to the minus 16 is still a small number and hard to explain. Dirac was the first to face this problem of large or small numbers that are hard to explain. He noticed that the proton mass to the Planck mass was 10 to the minus 19. He also noted 4 other large numbers, like the number of protons in the observable universe, which happened to be the 4th power, 10 to the 80, about 4 times this inverse of this number. Dirac said, why is this number so small? How could I possibly explain it? Well, his only explanation he could think, by the way, he could have invoked anthropic arguments. If this number were 1/100th, we wouldn't be here. 100 protons together form a black hole. So we can't live in a universe where the proton mass to the Planck mass is 10 to the minus 19. It had better be at something of order this magnitude in order to have enough protons to have stable stars without forming black holes. But Dirac was much too Dirac to invoke anthropic arguments. Instead, he suggested that all of these big numbers were related to one another by methods, by reasons he had no theory for, but they were related. And that remarkably led to a prediction. So the number of protons in the visible universe increases. So therefore, the inverse of this number should increase as well, and should increase substantially in a Hubble time. And so both the Newton's constant and the fine structure constant had time dependence, and that was a prediction that you could test, indeed, and rule out. And so Dirac's theory is wrong. Anthropic arguments, one of the reasons I don't like them, they might even be true, but I don't like them because you can never precisely rule them out, except by calculating. Well, in the case of Dirac's problem, we actually calculated this number, more or less. This problem was solved by QCD. The argument is very simple. You start with with a few assumptions, like forces are all going to be unified. Well, there's evidence for that at a very high energy scale. So the strong force is more or less like the electromagnetic force within a factor of 2 or 3 at this scale. That's the Planck scale. That's where unification shall occur. And then you run the coupling, the strong coupling, to lower energies. And it increases. That's asymptotic freedom. And that's what sets the scale of the nucleon, the distance in which the quark-gluon fields are confined, is set by the strength of the strong force. That sets this scale relative to this scale. And it's because the forces run logarithmically, it exponentiates. So because of the physics of the logarithmic running of the scale, to explain this number, you really have to explain the logarithm of this very small number, which is much easier and is naturally explained indeed by the running of the strong coupling constant. So we can calculate this number that Dirac was so 10 to the minus 19 within an order of magnitude. There are two other very small numbers or large numbers that we think we can calculate. We have ways of doing, like the mass hierarchy, the scale of the electroweak to the gut scale, 10 to the minus 16, slightly bigger than 10 to the minus 19, but it's also, hard to calculate, right? That's like the cosmological constant. Well, that we think, again, is logarithms, same old trick, with the additional physics of supersymmetry, for example. There's another very small scale, the neutrino mass scale. We think we have a different mechanism, seesaw mechanism, to calculate that very small number compared to the electroweak scale. So these are three examples of being able to calculate numbers of order, this incredibly difficult number to calculate. The problem is not the fact that it's small. The problem is simply we don't understand how to calculate it. But either did Dirac. Dirac had absolutely no idea of the physics that could explain 10 to the minus 19 ratio of the fundamental scale of nature, the Planck scale, and the size of the proton. Well, I don't know the answer, and maybe there isn't. But just because we don't know the mechanism doesn't mean that it doesn't exist. To conclude that there is no such understanding and that we have to resort to anthropic arguments is a little premature in my opinion, especially since all of the arguments are based on our present understanding of fundamental physics, including string theory, and we don't really know what string theory is. We have all these ways of constructing approximate solutions, but if you ask a string theorist, get him alone, get her alone, beat on hers. What is string theory? They'll admit they don't know. They don't know how to write down the basic laws. They'll give you various descriptions, the old 5 kinds of string theory, something called M theory, which we know little about, or some of the more modern and powerful descriptions of string theory, which happen to be old-fashioned field theories. In fact, field theories which are very close to the things we use in the standard model. So, could argue string theory is not any different than field theory. This is one of the failures of string theory. We don't really know what it is after 40 years. We don't really have a formulation. In physics, you understand a theory, sort of, when you can put it on a computer. We can't imagine putting string theory on a computer. We could put a calculation, a part of a perturbative approximation to the beginning of a construction on a computer. We couldn't put the theory on a computer. You just have an array of dual formulations, most of which are defined by perturbing around some consistent background. Something seems to be missing. Could be that string theory there's something truly missing. It's not a theory, it's a framework. Quantum field theory isn't a theory, it's a framework. And then you add symmetry principles or whatever to make a specific theory. What's attractive about string theory is that you don't have that possibility. There's nothing you can modify. But it also doesn't smell yet like a theory. We can't write down the equations or the principle. So it's strange. Maybe something's missing, but we don't know what it is. But maybe it has to do with, well, I'll come to that in a moment, the fact that we sort of need new rules. And we need new rules, to paraphrase Bill Maher, because we are faced with new questions that we really haven't had to or have the tools to begin to address before. In particle physics, the rules were formulated to answer the traditional questions of physics. What is the state of the vacuum now? And the small perturbations, excitations about the vacuum. How do we calculate experiments in the future given our knowledge of the present? But now, when discussing quantum gravity, discussing the quantum cosmology, we are force to discuss the whole universe. As Einstein stressed in a theory of gravity, a theory of the dynamics of space-time, the answer is not the state of the universe at a given time, the whole thing. The beginning, what happens at the boundaries, if there are boundaries, the end. And we've never had to face these questions before, but you can't avoid them in a theory of quantum gravity. None of our solutions, none of that landscape that people use to discuss the universe has a consistent account of either of the beginning and the end or the boundaries. What are the rules to construct a space-time history of the universe? And I don't think we really know what the rules are. We might not have the right framework for discussing those rules, which might be just as well, because in the framework we have, it's hard to imagine what the rules would be. We might have the right framework because many of us suspect that our understanding of the nature of space-time, as revealed by string theory, whatever it is, will have to change. Ed Witten said that space and time may be doomed, which scares some people. And Seiberg, I'm almost certain that space and time are illusions. Well, they're pretty good illusions, and I've gone much over one of them. But we have evidence within this theory that we discover, this theory that we've hit upon, and that is sort of unique, and you get what you get. And one of the things you get is the realization that space is an emergent phenomenon, that it's somehow not fundamental. It's a crude description of physics at large distances. And we have many examples in which one example in which all of space emerges as a large distance classical approximation to a different description. And a feeling, therefore, that if we ever had a fundamental description of string theory, whatever it is, it couldn't be based on space as a fundamental concept. But in relativistic theory, if we believe that space is emergent, then space-time must be emergent. Space and time have been unified since Einstein. And we have absolutely no idea, at least I have absolutely no idea, what it might mean to formulate physics without time. We have examples now where space emerges, all of space, all of the dynamics of space, gravity. But time, how would you start formulating physics without a concept of time? Physics is about predicting the future, moving in time, time evolution. It's about time. It's hard to imagine formulating, and that I think is one of the barrier to our inability to say what string theory is, because I suspect that to say what string theory is, it would have to be in a framework in which both space and time were emergent concepts. And that's very difficult, and will require a true conceptual revolution, which hasn't yet come, and probably is not right around the corner. So, to summarize, string theory has many hopes for the future. Unified theory of all the forces, new concepts of space and time, and maybe resolving these real paradoxes of quantum gravity and cosmology. These are difficult problems and will require true conceptual revolutions, I believe. So meanwhile, luckily, string theory has other things it is doing and can be usefully employed. It gives us incredible new insights into the kinds of theories we use in the Standard Model and elsewhere, into ordinary quantum field theories, especially gauge theory. Because of these formulations, sometimes, which can describe string theory as a field theory, as a theory of particles. Remarkable and useful. For example, the famous EDS CFT, correspondence between string theory and a curved space-time, 5 dimensions, And an ordinary gauge theory, much like the standard model gauge theories on the boundary of that space, in ordinary flat dimensions, space-time, 4 dimensions with no gravity, a large amount of supersymmetry, but that's not that essential, can be used to, for example, discuss properties of these gauge theories that are very hard directly, but easier using the string picture. And that's been used in some remarkable new applications now to discuss this quark-gluon plasma, and even in condensed matter physics to discuss quantum phase transitions in strongly correlated systems. Mathematics is another area where string theory has had incredible applications because it seems to, again, throw up new kinds of mathematics that are fascinating. New phenomenological scenarios, whereas string theory is not in a position to make predictions that could falsify the theory if we knew how to formulate the theory. It can give totally new ideas for where you might look for experimental phenomena, new kinds of experimental phenomena. And finally, coming back to the origin, especially with these relations between string theory and field theory, we might truly be able to construct the original motive for string theory, a theory of these meson flux tubes. So I'm going to go very quick through the possible new things that might happen, extra dimensions, lots of interesting phenomenological scenarios. Here there has been this QCD string, the string that, approximate string that describes these mesons, does, we believe, for sure now have a description in terms of a kind of string theory, which people are making enormous progress in constructing explicitly, and hopefully someday will be a useful analytic tool for describing these nuclear mesons. So, the message, we have a wonderful theory of elementary particles, but the most exciting questions remain to be answered. New accelerators and experiments are coming soon. They might discover quantum dimensions of space and time. Exciting new discoveries are around the corner. String theory has many successes, much promise, but because of its failures so far, the best is yet to come. Thank you.